All right, so let's get started. Welcome, everyone. I'm Danai Kutra. I'm a Morris Wellman Assistant Professor in Computer Science and Engineering. And it's my pleasure to introduce today our seminar speaker, Thorsten Joachims from Cornell. He's a professor in the Department of Computer Science and the Department of Information Science at Cornell University, and also an Amazon Scholar. Thorsten's research focuses on a synthesis of theory and system building and machine learning with applications in information access, language technology, and recommendation. And he's very well known for his work on counterfactual and causal inference, support vector machines, structured output prediction, among others. He's an ACM Fellow, AAAI Fellow, and a Humboldt Fellow. And over the years, Thorsten has won many prestigious awards, including 9 Best Paper Awards, 4 Test of Time Awards, and more recently, he won the 2020 ACM SIG-KDD Innovation Award. So before Thorsten begins with his presentation, I would like to say that you can post your questions in the Q&A, preferably not the chat. We'll be monitoring the Q&A. Alternatively, you can raise your hand and ask your question directly. Personally, I prefer this option to give some more interactivity in this remote format of the seminar. So without further ado, let's hear Thorsten's presentation.
All right, thank you very much, Danai, for the nice introduction. Let me share my screen.
Yes.
And it's nice that it's finally happening. The visit was originally planned for the Monday after Cornell closed down in March. You know, it's nice to finally make it work as good as it can be under these conditions. So what I want to talk about, so the title Fair Ranking with Biased Data is really only half of the story that I want to talk about, because fairness is partly a question of bias in the data, but it's partly also just a question of design, of how we allocate resources. And so what I want to do in this talk, I really want to talk about both aspects of how should we do rankings for the many different applications that we have today. And I want to question a little bit what our traditional approach to ranking is and why this would not be fair or desirable in the long run. So rankings are really just ubiquitous. We have rankings in search engines where we rank results in response to a query. We have rankings in e-commerce. So this is a query that I recently had for metal table legs. I wanted to have a new desk in my home office, and I think I actually bought these ones eventually, or something very similar to that. You all get rankings if you consume media, if you know, that could be movies, could be music. It's all based on recommendations and rankings. And much of the news that we consume these days are mediated through rankings. And this is how we do get our news. Now, I think I don't need to argue much more that rankings are very important and that rankings have a lot of influence. So let me think about what is the guiding principle that underlies these ranking systems. And I would argue that for that, we are still kind of stuck in the 70s. And so let me look back a little bit where rankings and information retrieval came from. It really came out of library science. And the earliest applications were about helping analysts or people visiting a library find the books that they want. And so I think Robertson in 1977 really brought it to the point that this view that what a ranking system is supposed to do, it's supposed to maximize the utility to the users, to the people typing in the queries. And he realized that, you know, by basically all different metrics of how you may want to measure utility to the users, discounted cumulative gain is maybe the most popular one, but precision recall, various measures like that. Basically, for all of these measures, if you rank the documents by the probability of relevance, that is the best that you can do. That maximizes utility to the users. And in many ways, I think that's what our learning algorithms that we now use to train these ranking systems still do. They are really trained to maximize the utility to the users. Now, let's think about in this talk whether this is really the most appropriate way of how to do ranking. So let's think about some of these applications. So here are my metal table legs at Etsy. Now, this retailer is really a matchmaker between suppliers and customers. So clearly, I draw utility when I go there and I bought these metal table legs. I draw utility out of that. I have a nice desk in my office now. I'm very happy with that. So the ranking here found me what I wanted. But there's also the other side of the market, right? There's the sellers, right? And when I bought those metal table legs, there was a seller that actually made revenue out of this. So the ranking that was presented influenced how much money the seller made. Or think about music streaming. Here's my Spotify account that got completely taken over by my kids. I use Amazon Music these days, so I get to keep a little bit of my own. So my kids get a lot of utility out of this, right? They find music that they like. And but it's also that the artists derive revenue, right? Whenever something gets streamed, the artist actually gets streaming revenue out of this. So by picking recommendations and by presenting rankings, our ranking systems influence which artist makes money. And my final example may be pretty close to home. So think about a recommender system for a scientific conference. Like we actually did build one for KDD this year. It's also a two-sided market, right? So there are the people who want to find interesting papers. Those are the users, and they draw utility out of the recommender system. But there's also the writers, right? That want to be seen and that want to be heard. And it's very important to them as well, right? If people read your paper, they cite you, you get tenure, or you get, your thesis widely visible. So many applications are really not like books in the library anymore, but they are two-sided markets where both sides of the market draw some utility from the ranking system. Now, maybe there's no problem at all, right? Maybe just maximizing utility to the users somehow automatically also provides some notion of maximizing utility or some notion of fairness also to the items, like to the suppliers, to the people selling on Etsy, or the writers of KDD papers, or the artists making music. So let's think about this and go through some examples and see whether we consider those fair. So here is a mocked up example where, let's say, we have a search engine that employers can search resumes over, right? So you're somebody looking for a job, you submit your resume to that database. An employer can type in a query like software engineer here and gets a ranking of candidates that they can now think about whether they want to invite for an interview. And let's say we know exactly the probability that each of these candidates will be invited for an interview by a random employer that comes in. And so here, like Adam has probability 50.99 of being invited to an interview, Bob 59.8, and so on, all the way down. There's lots of qualified candidates. And now we rank them by the probability of relevance because that, as we know, optimizes basically any utility metric that is relevant to the employers. Now, what's going to happen here if we present this ranking? Well, Adam is the most relevant one, has the highest probability of an interview. And we put Adam in position number 1. Everybody's going to see Adam. He's probably going to get a lot of invitations for an interview just because lots of employers see him. But then there's lots of qualified candidates. Like in position 100, there's Alice. And she also is basically just as relevant as Adam, just a tiny little bit less for some reason. But nobody is going to see Alice in position 100, right? So Adam gets very high exposure. Alice gets very low exposure, even though their difference in relevance is only epsilon, is only very marginal. You know, that would be unfair, I would argue, right? They have almost the same merit, but they have very different, there's very disparate impact on their chances for success of getting an interview. Now, you know, you probably already noticed that somehow all the stereotypically male names are at the top and all the stereotypically female names are at the bottom. What's actually happening here is not that Alice is any less relevant or less qualified than Adam. It's actually that like 2% of our employers are just biased. They will never invite a woman for a software engineering position. So, you know, if 2% of our employers are biased, that, you know, drags down the probability of an interview for all the women by roughly 1 percentage point. But this small bias in a small fraction of our employers now has a really big influence on a woman getting invited for an interview, right? So what our system is really doing is it's amplifying existing biases that may exist in your data in a very undesirable way. So that's definitely something that we don't want, right? We don't want our ranking systems to make existing biases even worse and reinforce them. Let's look at a different domain. Actually the same numbers, right? Now it's music recommendations, and there are different artists A1 to 102. The probabilities are exactly the same, and now it's the probability that I'll enjoy it, that I'll enjoy that artist. Artist A1 has the highest probability that I'll like it, but you know, there's lots of really good artists, and if the system consistently ranks these kind of probably very popular, already popular artists first, you'll get these rich get richer dynamics, right? You're creating these, what the Spotify people call superstar dynamics or economics, where, you know, if something is at the top, it gets even more exposure, more people will like it, it gets more to the top, right? And so you're creating a market where you have a few superstars that make a lot of money off the streaming revenue. And then you have a lot of artists that actually produce very good music and that never get found and that probably don't make enough money to make a living. So as a streaming provider, you may not want this, right? You probably don't actually want this, right? You want to have a rich market. You want to have a lot of good music being produced. So you may have, as a streaming provider, have an interest of not creating these winner takes all kind of dynamics and rich get richer dynamics, but to distribute revenue more broadly. And I think would argue that this is more fair in this context as well. And again, if people have questions, you know, feel free to just chime in. I'm happy to take questions also throughout. And maybe my final example is maybe news stories. Maybe there's just two news providers here in my mock-up example, the Times and the Post. And again, the probabilities are exactly the same as before. Maybe the Times is more liberal, the Post is more conservative, and maybe there's just a tiny bit more liberal readers coming to my platform. So that would mean that the probability of read for the liberal outlet newspaper is higher than for the conservative one. But it's clearly not desirable to rank all of the Times articles above all of the Post articles, right? That will alienate all of the conservative readers, and will probably they will rightfully claim that your system is biased against them. So again, there would be a perception that this is not fair. So I think, however you want to slice it, different applications would have different phenomena. But I think in many cases, just ranking things by probability of relevance to the user does not automatically create fair or desirable rankings from the perspective of the items, and sometimes even not from the perspective of the users either. And sometimes it's just kind of blatantly unfair. And sometimes it's that it would create long-term dynamics of the system that you don't want, right? That would be detrimental in the long run. Like it would lead to a concentration of the of the music market, for example. So we have to do something in addition. And what I want to explore in this talk is kind of two different aspects of fairness that I think are often kind of mixed together, but that I want to tease apart and try to address separately, but also at the same time. And so what I argue is that one aspect of fairness is that we need to be explicitly fair to the items that are being ranked, and that we need to make this kind of allocation of exposure, because that's really what a search engine, what a ranking does. It allocates the scarce resource of exposure among the items, right? There's only limited kind of eyeballs or limited attention that the ranking system gets to distribute, and it needs to do this in a fair way from the perspective of the items. And so it needs to be based on the merit of the items in some quantifiable way. Merit, for example, meaning relevance here, or probability of being invited to an interview, or probability of being enjoyed. And so there are two aspects of this. One I call endogenous factors. And that's really what the last slide was about. We knew everything, right? We knew exactly, what the probability of an interview was. We knew exactly what the probability of relevance was. But we need to think about, how do we now allocate exposure based on the knowledge of the merit? And there we may have legal requirements. So for example, in the job application example, there may be legal requirements that in certain jurisdictions actually say you're discriminating against women, you're not allowed to do this. In other cases, like in the music domain, you want to shape market dynamics in a particular way to have an overall dynamic of the system that's beneficial. And in some other cases, it is actually a way to also control spam or polarization or other effects that you want to mitigate. So this is really a design problem. Then there is also a statistical problem, right? We typically don't know exactly what the probability of relevance is or what the probability of an interview is. We need to estimate it from data. And so we need to make sure that our biases, that our estimates are unbiased. And there are different sources of bias here. There are biases that come directly from how I've presented results in the past. Then there are biases that are like ingrained in kind of the behavior of my users that I'm learning from, like stereotypes. One of those, I only know how to handle one of those, or maybe two to some extent. So let me talk about one of them. That's the position bias. But before I do that, let's first talk about this case of exogenous factors. How do we design ranking policies if we know everything about the, if we've kind of solved the biased estimation problem? Okay, so we need to quantify this thing of exposure. I said that we're allocating, that we have this resource that's called exposure that we need to allocate among the items, right? So we need to quantify that. We'll use the simplest exposure measure that you can probably think of. Basically, what we're going to say is that if you put something in position 1, a certain fraction of users is going to see it. If you put something in position of 2, a certain fraction, E2 of users is going to see it. In position 3, a certain fraction like that. And you get a decreasing curve like that you can estimate. There's different ways of how you can estimate that. You can, naively would be to do it via eye tracking, but you can do this, in multiple clever ways. You can estimate this drop-off curve of how many people are going to see something if you put it in position K. And then the exposure of a group of items. So for example, all the products that a particular seller on Etsy sells, or all the tracks by a particular artist, would just be the sum of these exposures. If you put something in position 2 of a particular artist in position 2 and 100, you would sum up, whatever these two E values are, and that's the exposure that this group gets. You can think about more sophisticated models, but this is, that's a start. So we've defined exposure, and now we have to think about how do we allocate exposure. So we'll have explicit goals where we are saying that we want exposure of a group, like all the products of a seller, for a particular query X, to be a function of the relevance, of the merit of that group of items for this context X, for this query X. And so we get to design this function F. And for example, one particular function F that we could implement that is probably a reasonable one in many cases is that we want exposure to be proportional to relevance, right? If something is twice as relevant, it should also get twice the exposure. If two things have almost the same relevance, they should also get almost the same exposure. But you could really make this also, it doesn't have to be proportional, it could be something else. If you have this function F here, you can turn this goal here into a disparity, right? You just say, instead of having this be equal, you take the difference between the two, take the absolute value, and then 0 would be optimal, but you can allow some error, right? And so eventually we will want to minimize this disparity. So now we have a target of what we mean by fairness, right? We want this kind of specific allocation of exposure based on the relevance of the items. So we can now formulate this as a new type of training objective. So we can go with the old objective, of we want to maximize the utilities to the users, but we want this additional constraint that says the disparity, this fairness disparity, should be less than some delta. And this delta is something that we can set as a parameter. Now, these two expectations we of course don't know, but we can approximate them just as we always do in empirical risk minimization with an average over our training data. So utility is an average, and disparity is also an average over our training examples. So we can write this as this constrained empirical problem of maximizing utility subject to estimated disparity being less than delta. And if you just put in a Lagrange multiplier, you can get rid of this constraint and turn it into an objective where this Lagrange multiplier lambda here becomes a parameter that you need to set. And it kind of regulates the trade-off between how much utility are you willing to sacrifice for minimizing disparity or maximizing fairness. So that's an objective. So this is what we kind of want to optimize in our machine learning algorithm. Now, we haven't talked at all about what these policies, these ranking policies are. And if you think about it, rankings are these discrete objects that are really nasty to work with, right? You can only like move a thing up 1 or 2, and then you get this jump. And you could probably never really get the disparity down to 0 because it's like everything works in these discrete steps. So the key trick that we're using is that we're not using deterministic ranking policies, but that we're using stochastic ranking policies. And they made our life a lot easier. So a stochastic ranking policy, pi of a ranking y given a query x, that's just a conditional distribution over rankings. And a deterministic ranking policy is just a special case of that, where one particular ranking has probability 1. So like here's a visualization of a stochastic ranking policy. You maybe have just 4 base rankings here, y1 to y4. And with 52%, you present this ranking. With 23%, you present that ranking. With 20%, you present this ranking, and 5%, you present that ranking. And so the ranking that you present now in expectation becomes this mixture of rankings. And that lets you kind of smoothly change your rankings, and you don't get these discrete steps, right? Just by fiddling with these probabilities down here, you can kind of interpolate between rankings in a smooth way. The utility can just define, as you would expect, right? You just take the marginal probability over this distribution of rankings pi of a ranking policy. And exposure, we can also define over stochastic ranking policies, right? So we just take the marginal probability that something ranks, that a particular item j ends up at rank, a particular item ends up at rank j. And so, for example, that the item A ends up in position number 1 is 52 plus 20, so that's 72% probability, right? That A ends up in position 2 has 23% probability, and that it ends up in position 3 has 5%, and all of the other position has 0%, right? And so we can kind of calculate this expected exposure as well. So now we have a utility measure, we have a kind of a disparity measure, we have a space of stochastic policies that is nice and smooth. Now we can optimize this directly in the space of policies. And in particular nice space of policies is these Plackett-Luce ranking policies. Plackett-Luce model is a way of generating a probability distribution from scores, and it's a very simple one. Each item you estimate a score for, and it's like you have a deep network that outputs a score for each item that you want to rank, just like you always do. And this score for item j is this Sj here. And then to generate a distribution of rankings is that you take all of your scores, and in the first position, you draw from the score, proportional to the score, the item that you put into the first position. Once you've drawn that, you take it out of your pool, and over the remaining items, you draw proportional to the scores what you put into the second position, and so on, third position. Your pool gets smaller and smaller, and that's just how you fill the ranking. That gives you a very nice kind of tractable way of generating or sampling rankings. And it turns out when you can sample rankings, there's nice old tricks to estimate a gradient in your policy space that people have used in reinforcement learning for a long time. So you can get Monte Carlo estimates of the gradient with this kind of reinforced trick. And then you can use other tricks as well to make the training problem well-behaved, like entropy regularization variance and different ways of reducing the variance of the gradient as well. But basically what you can do, if you have this space of ranking policies, you can directly optimize this objective by doing stochastic gradient descent. So that kind of completes that we actually now have a fully specified learning algorithm for training policies that can also kind of take fairness objectives into account. So we can try this out on some experiments. This is semi-synthetic data derived from the Yahoo Learning to Rank challenge data set, where we now have, we want to make exposure proportional to merit. And here we assume that we know that we have fully labeled relevance judgments that are given in this Yahoo Learning to Rank data set. And so we use a deep network for learning these scores, and that gives us these policies through the Plakat-Luce model. So this graph is, if you now crank up this fairness parameter from I don't care about fairness to I care very much about fairness, then what happens is that the disparity, or the negative disparity here, if you make this parameter strong enough, eventually you get something that becomes more and more fair. And at the same time, your utility to the users, here measured by NDCG, it does decrease at some point, but there's definitely some sweet spot where you gain a lot in terms of fairness, and you haven't yet lost a lot in terms of utility. So somewhere around here may actually be a good operating point where your solutions are substantially fair, and you're still you haven't sacrificed that much utility. What is it actually learning when it's doing this trade-off here, right? So I said, the utility to the users eventually goes down, but what is it actually doing? Well, to some extent, it's increasing stochasticity, and that's beneficial from the perspective of fairness, so that we don't statically rank one above the other, even though they're really close. But you're also able to now detect whether you have biased features. So I think one thing that's happening quite frequently in data is that you have some features that are informative for some group of examples or users or items here in this case, but that are uninformative for some other group or less informative for some other group. And here's a little toy example where we have two features. The feature feature 2 here and feature 1 down here. And what the shading in this graph shows is the utility of the solution. If you set feature 2 to this value, or the weight of feature 2 to this value, and the weight of feature 1 to this value. So you get a high utility solution. And that's what you get if you don't care about fairness. So this lambda is equal to 0. Here, this plot shows how unfair the solution is. The darker red, the more unfair. So here you see that you have quite a lot of unfairness. If you crank up the lambda, your unfairness goes down because the system now realizes that it shouldn't rely so much on this feature 2, because that feature has a disparate informativeness for the two groups. And so it should focus on that feature 1 only. And so it gives proportionally more weight to feature 1 than feature 2. That also decreases utility, but that's where you get this trade-off from. So it's actually very important to train these systems end-to-end, I believe, because only if you do this end-to-end training can your learning algorithm actually detect that you have some biased feature and appropriately correct for this bias. So that was one aspect of we know everything about, if we actually have clean data, how do we design ranking policies that allocate exposure based on the merit? But now let's go to the exogenous factors, where we now have not clean data. It's more like, we have these biased employers that actually, express their bias. I don't know how to handle that, but I know how to handle position bias. And position bias is something that I think you always have when you're dealing with online systems, because the way that you're presenting the results biases where you collect data. And so it often leads to these rich get richer dynamics. So let me explain what I mean by this and how we can mitigate this position bias. So the data that we typically get from ranking systems looks kind of like that. So in the past, we've gotten queries, we've presented rankings, and we have observed clicks on these rankings. But clearly, our deployed ranker has a big influence on where we see clicks, right? We'll see clicks at the top of the ranking. We are not going to see clicks at the bottom of the rankings, just because people don't look there. So the feedback, the clicks, the purchases, the plays, the reads, they're all biased by what our ranker did that we used when we collected the ranker, when we collected the data. So if we don't mitigate that, if we just counted clicks, right, we would naively say that, whatever we've put into position 1 in the past, it will just stay there. It's going to get the most clicks. And something that is perhaps even better, but further down below, is never going to be able to catch up with this, just because people don't see it at the same rate. So that's the fundamental kind of aspect of position bias. And we need to think about, how do we now debias the data? How do we take into account appropriately that some items have less probability of being seen? Let's go again with the simplest model, and it's the position-based bias model. And let's assume that the following holds. People click on an item if they see it and if it's relevant. And the other direction as well, if you see it and you find it relevant, then you will click on the item, right? I think that's a plausible kind of relationship that, at least at the first order approximation, models how people behave, right? Or how this data is generated. So that's all good and nice and easy to work with. So if we see a click, we know that the user must have looked at it and that the result was relevant. And I'm not going to go into detail about long clicks and short clicks and clickbait, and you can correct for that separately as well. And you have to worry about it. But where's the problem here? The problem lies when we don't see a click, right? Then there's two different causes for this that are possible. Either the user didn't see it, and that's the reason, or it wasn't relevant, and the user saw it but didn't click on it, right? And what we really want, we only want to count the clicks based on relevance, right? We don't want to kind of the observation, whether somebody sees it, is really just messing with our data. It's biasing our data. So this observation mechanism kind of confounds the relevant signal that we like to measure. So we need to correct for that. And we can't observe observation, right? It's impossible. We would have to put people like into eye trackers, and that's just completely impractical. But it turns out that it's not necessary to do this. We don't actually need to know exactly whether somebody observed this result or not. In a sense, we only need to know the probability or an expectation whether something is observed or not. So again, the simplest model to work with here is, if we know the probability that a particular item was observed when the data was collected, then we can use that to debias the data, and bias being something that is an expectation. So let's say that we have this very simple, and we call these propensities, the probability that something is being observed. So let's say we have this propensity model where we know that for this particular query, the item in position 1 had a probability of 1 of being observed, in position 2 a probability of 0.8, in position 3 0.5, and so on. Then, and that's exactly the exposure probabilities that we had before, right? That's exactly the same thing here. We can use these inverse propensity weighting techniques from causal inference to debias our utility, for example. So this is a generic way of writing very many utility metrics, for example, discounted cumulative gain. And the basic idea is very simple. If I see a click, let's say on the third result, and I know that only half of my users go down there, then every time I do see a click, I just double count it, right? And if I see a click on F, and I see that only a fifth of my users go down to that position, then every time I do see a click, I multiply it with 5, right? I gave it a weight of 5. And you can kind of see intuitively that in expectation, I'm now doing the right thing, right? I'm correcting for the missing data. By every time I actually do observe it, I upweight it appropriately. And that gives me data as if I had full information in expectation. So I get unbiased estimates of the utility. And I also get unbiased estimates of the relevance of an item, right? Or let's say of the items of a particular group, right? All the items of a seller, for example, right? I can use these weighting techniques to get these unbiased estimates, even though my data is biased. But because I know the missingness mechanism, I can correct for the selection bias. So that now gives me estimators that are again unbiased, and I can do empirical risk minimization with those, right? So I can use the same objective that I had before, but instead of having these full information training objectives where I needed manual relevance judgments to be able to compute them, I can now estimate them with from click data with these inverse propensity weighting techniques. And the same thing, I can also estimate disparity. Well, disparity, not completely, because it is an unbiased estimate for each query, but it has huge variance. So what we are doing here is we're really aggregating to a kind of amortized relevance of a group of items, amortized over many queries. And so it becomes a little bit similar, or actually quite similar to what Biega and al. Did in terms of their amortized group disparity that they've introduced in 2018. So, but you get this disparity measure that takes the form like that, which is something that we can, again, estimate. And asymptotically, we get a consistent estimate of this disparity. So now we can use the similar kind of techniques of policy gradient, Plackett-Lucha model, and estimate and directly work with click data that is now unbiased and that we can optimize directly. So these are again experiments now on again on a standard benchmark for learning to rank. Again, we use this amortized proportional exposure disparity that we want to optimize, or that's our constraint. And this is just a Plackett-Lucha model with a linear score, not a deep network here. What this plot explores now is if you have perfect data, full information data, manual relevance judgments, then you get this dashed curve here, where you have the utility to the users in terms of DCG on this axis, and unfairness disparity on this axis. So what you get is, if you don't care about unfairness, you get high unfairness. But then actually pretty quickly, you can drive unfairness down with quite little on this data set, quite little loss in utility to the users. And you can actually drive it to 0. That's if you have full information data, not click data, but somebody gives you the true relevance labels. Now, if you only get click data, if you have a little bit of click data, you get this curve. If you get more and more click data, you eventually actually very well track the curve as if you had full information data. And, just as the theory predicts. So with enough click data, you actually get kind of the same type of behavior that you would get if you actually had very expensive manually labeled data. Here's a comparison to other methods. Group blind, that's this green dot here, that basically says, let's just ignore. So we had an attribute in there that would tell you, is it group 1 or group 2? And group blind just takes this attribute out and hopes that somehow through that you would get a fair solution. Many have noticed already that this just doesn't work because group membership is encoded in many other different features. So this is, it doesn't give you a fair solution. Here's a post-processing technique. That's the paper by Biega et al. That I mentioned before. They assume that you know the true relevances, which of course you don't. You need to learn them first. So if you do first a regression to estimate relevance, and then you post-process it to be fair, it doesn't actually work. So even if you crank up they have a parameter in there as well that says, yeah, make it more fair, make it more fair, make it more fair. It doesn't actually become more fair, it just becomes worse. Because the estimated kind of relevances were already corrupted by the position bias. And so you're actually optimizing the wrong thing, and it doesn't do anything sensible. The same thing for fair PG-rank. That was the method from the first part of the talk. If you just naively say clicks are relevant, not clicks are not relevant, and then run that method on there, it goes completely bonkers. It actually makes, if you say make it more fair, it actually makes it more unfair, just because, again, it doesn't know about the position bias. If you train explicitly with the model of the position bias, either a linear model or here deep network, that's then you actually get that you become fair, and especially if you have a very high capacity model, you actually even the initial unfairness wasn't actually that high. All right, so the main point that I wanted to make is that fairness in these ranking systems, actually there's many different factors. There's the biases that you have in your data that you need to take care of, but you really need to also think about the policies that you're encoding in your ranking system. So just ranking by relevance is typically not what you want to do for many different reasons. And let me just give an outlook that this is just scraping the surface of what it means to present fair rankings. I think we're seeing more and more applications of these methods that we developed for recommendation in the online domain, like that we developed for recommending movies or recommending music, right? Which are pretty inconsequential decisions for the people involved. In aggregate, there may be quite consequential to like an artist or a seller, but each individual decision is actually pretty small, right? But we are taking these techniques, I think increasingly, and applying them to consequential decisions, like college admissions. That's something that I'm actually working on with our admissions office right now, or job recommendations. And there you have matching markets, right? Where it's not only that users have preferences, but employers have preferences too, right? In many of these other examples that I gave, really the artists don't care who listens to their music, or the seller on Etsy doesn't care who they sell to, right? But here now you have this match that the preferences of an employer have to match the preferences of an applicant. And only if both like each other do you actually have a successful match, right? And if you think about these matching markets, you get highly complex optimization problems, right? What does it even mean to optimize a ranking in this setting, right? And there are many different perspectives to take. One is, how well off is each individual applicant or each individual employer? But there's also a social welfare that is or kind of again, a market that this creates, right? So as a society, in a job recommendation example, we have an interest that as many positions get filled and as many people find a job as possible, right? So there's an overall objective that we have for the system as well. And so we've started to look at, can we actually optimize these matching markets and derive and come up with rankings that are optimizing some notion of social welfare in these systems? And just this one slide to illustrate how complex these problems get. So this is synthetic data. And the red bar is if you optimize the rankings both for the employers as well as for the job candidates in a way that you're saying, well, maybe this, this candidate should really apply here for this job because I think that employer is going to like this candidate. And it's not a job that's too overcrowded, so there's actually demand there, right? If you try to optimize all of this in big, complex optimization problems, compared to just naively ranking by relevance and having some jobs be overcrowded and other not getting any applications, then you actually get quite an increase in kind of the number of jobs that get matched, right? These are the red bars in different scenarios. These are just different synthetic settings here. So there is a big potential gain there. We could probably connect a lot more people with jobs. But on the other hand, you also have now fairness problems or issues with the individuals, right? If you look at, some people a lot of people are better off in terms of their individual utility that they derive from this ranking from having an overall optimized ranking, but some people are not, right? So there's a fraction here that is actually worse off. And how do you make sure that you make these trade-offs in a fair way? I think these are big open questions. All right, so with that, let me wrap up. So I think there's an exciting research agenda there that's, I think, extremely important that, we have all of these ranking systems that are becoming more and more ubiquitous everywhere. And I think we have to think about all of these additional objectives that these systems have, in addition to our kind of good old training objectives of just maximizing utility. So if you're interested in some of these papers, feel free to come to my website, and they're all somewhere on there. Thank you.
Great. Thank you, Thorsten, for the very interesting talk. So we'll start with the Q&A session. Just a reminder that you can post your questions in the Q&A, or you can raise your hand and ask your question directly. So there is a question about, is there work done to see commonalities between items that were ranked lower but ended up being clicked on or selected?
I'm not sure I understand the question. So, I mean, partly it's, so if you see something that's ranked low and that gets a lot of clicks, that's certainly a signal that it should be ranked higher, right? In particular, what this inverse propensity weighting really does, it gives the low clicks a boost, right? It makes them more important in your training objective. So if something is low and gets a lot of clicks, if you train on that, it would certainly be boosted up much stronger than if you didn't do this kind of correction for position bias. And that would kind of let you learn a ranking function that maybe identifies that, somehow, you didn't properly account for some aspects of these items, and that, what got clicked on here, maybe there are other items that have similar properties that also should be ranked higher.
Mm-hmm. Yeah, so I also have a question about the first half of your talk. So there are a lot of different definitions of fairness, and I was wondering if it is possible to change the formulation to incorporate different definitions there.
Yeah, it's actually, I mean, there's fairness to the items. There's also fairness to different user groups, like people have looked into problems of, if you are from a minority group and you are coming to a system, then you're probably getting worse utility than if you're part of a majority group, right? If you're in a minority group, you probably have to shoulder more exploration, right? All of these systems have to do exploration for doing learning. You have to shoulder more exploration. So there's fairness to the items, there's fairness to the user groups, there's diversity, which often gets lumped in together with fairness as well. I think those are actually different concepts. And in many cases, I think it's beneficial to keep them separate. So we've just actually started to look at, can you actually achieve all of these objectives at the same time? Can you be fair to the items in allocating exposure to them? Can you be fair to different user groups? And can you also be diverse? And diversity being now about kind of minimizing variance between queries across users. That's typically done in extrinsic diversity. I think you can, but it's additional constraints that you would be adding to your training objective. And I think in many cases, maybe the algorithms generalize. So some of these kind of policy gradient algorithms you can extend to these settings. But I think there's a lot of definitions of fairness, but I think they're not necessarily an or, but they're an and, right? That there are multiple aspects of what can be unfair. So
yeah, thank you. There's another question from an attendee. In your college admissions project, what types of exogenous bias are you attempting to correct for? And they're thanking you also for the great talk.
Yeah. So in that project, that's still kind of in the initial stages. We are currently we're currently making the assumption that we are actually happy with how currently admission is done. And it was done in a very labor-intensive way in the past. So all the folders got read, very careful consideration. And for example, Cornell engineering does admit a class that is very gender balanced. So what we're trying to do there is that we're focusing less on correcting for biases, because we believe that we are actually reaching the kind of the standards that we want already, but we want to make sure that we can do it more efficiently and that we're not wasting so much time on, let's say, applications that don't actually need that careful review, so that it frees up time to be even more careful with others. And so there the aspect, there it's mostly about how do we learn to better identify applications that need to be prioritized for review, so that we can then kind of allocate the manual effort in a more meaningful way. So it's less. So we're basically assuming that the exogenous bias there is minimum, and we don't need to worry about it.
Mm-hmm. Great. So we are a couple of minutes past 5, so we understand if some of the attendees need to leave, but there are some questions coming in. So I'm taking the liberty and continuing a little bit more with the Q&A, if you don't mind. So Abdu Zokbi is asking how much of the improvement you find comes from the stochastic ranking as opposed to modeling the disparity explicitly?
It's hard to quantify. I don't actually know how much. So the stochasticity leads to just some general blurring, right? Which helps, especially if you have something where items are like epsilon apart in terms of relevance. Once you introduce stochasticity, it really kind of does these kind of pairwise swaps very nicely. How much its effects like that versus kind of learning about that certain features are biased in certain ways. It's definitely both going on, but I don't know how to quantify it. I don't know.
All right, and then Eric Golub is asking, what is the relationship between fairness of search results, filter bubbles, and political polarization?
Yeah, so I had this as an example on when we're designing these allocation policies here, that I think some of the objectives that we may have is, for example, mitigating spam and polarization. I think what's currently happening is that some of these winner takes all kind of rankings kind of create or definitely support filter bubbles in the following way. I may have I may like or I may be maybe 10% more likely to read a liberal leaning news source. But if I went by just ranking by probability of relevance, that would really put me into a completely liberal filter bubble, right? But maybe I do have a 40%, actually I do, right? I want to read conservative sources as well. So if you went by probability ranking principle, I would probably get an all liberal diet. Whereas if I went by fairness of exposure, I would get a 60-40 diet of liberal versus conservative, right? So just by changing some of these allocation policies, I think you wouldn't have these very strong self-reinforcing effects that you get from these kind of conventional rankings. I think actually also for kind of search engine optimization spam, if it's currently it's extremely valuable to make it into the top position. If you had an exposure allocation scheme that would be more proportional, so you just need to be epsilon better than the second result, right? And people are willing to spend a lot of money to become epsilon better than the second one. And that pays off handsomely under the current allocation strategies. If you had proportional allocation, then being epsilon better than the second guy only gives you epsilon more exposure than the second guy, right? So it would actually, I think, quite drastically change the dynamics of how valuable or how much it pays to spam and to optimize your search results. I don't know how much of an effect this would really have, but it's an interesting thought experiment in the least.
Thank you. And let's take one more question. How do you handle tolerance sensitivity? I would expect ranks to be relevant only within a tolerance sensitivity set. Beyond a certain point, the rank is irrelevant. Exposure is 0 regardless of rank.
Yeah.
The main question, how do you handle tolerance and sensitivity?
Yeah, I mean, many of these exposure curves are basically that they flatten out. And then, after position 50, maybe it's even 0, or it's like epsilon all the way through, right? Or it's probably just 0, which is actually doesn't break anything in this model. It just means that when you now have a stochastic ranking policy, you kind of need to promote things into the kind of top K that are actually visible with the right probability. Yeah, I'm not sure what tolerance means. There's actually an interesting other aspect as well that we're looking into, and that is whenever you have these, basically you're making point estimates of the merit. How what's your estimated relevance of an item? But for some items, you may be more certain than for others. And so I think it would make sense, for example, maybe that's what you mean by tolerance and sensitivity. It would make sense to model the uncertainty of your estimate as well, right? So that if you have an item where you estimate maybe the relevance is here, but with a lot of uncertainty around it, that you wouldn't always put it at this position here, but you would recognize that, hey, sometimes it should actually, it definitely has a chance to be in the top position. And that you would try to kind of reflect the uncertainty in the rankings that you're presenting as well. So that would potentially also mitigate some of the effects that you have that, for certain groups, you can estimate relevance better than for others. So instead of always going like with the point estimate, that you at least model the uncertainty.
Great, thank you. So since it's 5:10, let's conclude. I'd like to thank you again for joining us today. I'm glad that we found a time that worked out. And thank you for presenting your very interesting work. I'll clap here for everyone, all the attendees. Yeah. And thank you everyone for attending the seminar.